Welcome back everyone. In the last lectures, you have seen what are PID controllers, how we can tune them, what are the different methods of tuning, and also we saw the different problems that PID controllers faces during implementation. Today, we will see PID controllers in action. Basically, idea is that we will take two systems, one being the DC motor and we will try to control the speed of the motor, and the other being a drone where we will try to control the altitude of the drone. In both these cases, we are not going to go into the transfer functions or the Ziegler-Nichols method that we have talked about. It will be purely based on intuition, and the reason I am showing you this is to show the power of PID controllers. In other words, even if you do not know much about PID controllers, just by understanding how the P, I and D part works, you can go ahead and tune the PID controllers. So, to recap, proportional controllers were these type of controllers where the output of the controller directly depended on the error signal, which means the output of the controller is proportional to the error signal. Whereas the integral controller was a controller where the output of the controller dependent upon the integral of the error signal. I have already told you that we use the integral controller for eliminating steady state error. Whereas the derivative controller was the one where the output of the controller is a derivative of the error signal, and we use this to reduce overshoot or rapid changes at the output of the plant. So, we will try to see this, we will try to implement these controllers for the DC motor first, where we are trying to control the speed of the DC motor. So, I upload the code. Remember, in this case what is happening is, once you have uploaded the code, the Arduino will keep on waiting to get the PID gains. So, here are your Kp, Ki, Kd gains. So, the Arduino will wait for these gains. Okay. Once you put these gains in MATLAB and run this, so the Arduino will get those PID values and then this will get implemented on the motor, so that the speed of the motor gets controlled. So, let us go ahead and look at this. So, if I give Kp equal to 0.3, as you can see here, and Ki and Kd is 0, where the set point here is 15. So, basically I am looking for 15 RPM. So, let us see how does the output or the DC motor behave. So, here we have this DC motor and you can see that this was your set point and the DC motor speed here is not reaching the set point of 15 RPM. Okay. So, now I will increase the value of Kp. So, what do you expect when I increase the value of Kp? As soon as I increase the value of Kp, that means the output of the controller now becomes Kp into Et, where your Kp value will now become 1.2. So, which means the response would be faster, and you can see that here. You can see now that the motor is oscillating faster. You can see this, right? Lot of oscillations are going on because you have increased the value of Kp. So, the response is much faster now. However, there is oscillations which is again not desirable. Now, if you see oscillations at the output or too much of change at the output, you want to curb that, you want to bring that down, and for that we know already that a D controller should be used. So, we will use the PD controller now. So, I am changing the value of D to take care of the oscillations. See, all this I am doing intuitively, there is no calculations here, just by looking at the response I am doing it intuitively. Okay. Because this is a DC motor, I can look at the response and do it, but you cannot do it always. I mean, always you cannot implement the PID controller on the system and check how the system will behave, right. So, in those cases you have to go for analytical approaches. in this case we can actually go ahead and see what the output looks like. Since it was oscillating, I am putting a value of Kd to be 0.1, and you will see the response should die down, or the oscillations should die down. You see the oscillations have died down now, you can see that, but you can also see that still the output has not reached the 15 rpm value. Okay. Now, here I would like you to think about something. What are we trying to do? We are trying to control the speed of the motor. So, if you remember theoretically, when we found out the transfer function of the motor, the transfer function of the motor came out to be a type 0 system. So, since it was a type 0 system, we know that the steady state error will always be there when you give a step input to the system, and that is what is happening. So, now I will take care of the steady state error by introducing some I component, and as I introduce the integral component, of course, remember these values that I am giving, we have tried and tested this, we have kept on iterating and came up with these values. Okay. You have to keep on doing this for some time. So, you can start with a smaller value of Kp and then accordingly you can change. Okay. Since we have done it quite a lot, so we know what values we should use for this system. So, if you are new to the system, this will take some time, it will be an iterative process actually, you will have to keep on doing this. So, now you can see that the speed actually reaches 15 rpm. Okay. So, this is how we can design the speed controller of a DC motor. Similarly, one can design position controller for a DC motor as well. So, this is the position control of a DC motor setup. Here what we are doing is that we are giving the desired value using the knob here. Okay. Basically, the amount of angle that the knob turns will be the reference position or the reference angle to which the DC motor shaft should rotate. The P value will be changed by these values PID, and you will, so here you can see that I have increased the P value to say 0.428 here, and then I am changing the desired. See, as I change the desired, the shaft of the motor is also rotating. However, there is a delay between the rotation of the knob and the response of the shaft. Okay. So, here there is a sluggishness that we are seeing. When you are rotating the knob, the shaft is not rotating at the same instant. So, there is some delay, and that can also be seen from the plot here. Here the red line is your reference signal and the blue line is the position of the shaft. So, now what we will do is we will increase the value of P. So, you can see I have increased the value of P now to 2 almost, and now you see as I change the desired position, you can see the response is much faster. If you look at the shaft also, you will find that there is a little oscillation. Okay. You can see a little oscillation is there, that can also be taken care of if you increase the D a bit, but more or less this is looking fine. Now we will increase the D a bit because there was a little oscillation that we saw. Let's try to get rid of that, and you can see that now that oscillations are gone and the output is also exactly following the reference trajectory. Now, let us move to the case of a drone. Okay. Now, here you can see we have a crazy fly drone here. Okay. And in this setup, I have already divided the plot into 4 parts because we will be using different controllers. So, what we are trying to do with this drone is that we want to control the altitude of this drone. Okay. So, if I have to control the altitude of this drone, I have to change the values of the PID controller that I will use for this. Again, theoretically, if you remember, if I am just controlling the altitude, the transfer function is 1 by s square with acceleration as input, and we know that a PD controller should take care of this. But you will see that this will not be the case practically, because when the drone is flying, you will see that the drone is moving in the xy direction also. Okay. One thing that you need to remember is that the drone does not have just one PID controller. It has actually lot of PID controllers, because there are 3 directions. So, you will have lot of PID controllers. So, I am just concentrating on the PID controller that takes care of the altitude. Okay. When we will talk about drones in details, you will see that there are almost 6 to 12 PID controllers that will be present in the drone. Okay. But here I have fixed all the PID controllers except the one that is changing the altitude. Okay. And that for that PID controller, I am changing the values of P, D and I to show you the effect of that on the altitude of the drone. So, now what we are doing is we are starting with Kp equal to 5, and let us see what the response is. Okay. My reference is 1.2 meter. I want the drone to move to 1.2 meter, and you can see that the drone is more or less flying fine, but of course, it has not reached the value of 1.2 meters, and also the response is a bit slower. So, what we can do is that we can increase the value of Kp. I have increased the value of Kp to 13 now. You can see that the value of Kp is 13 now, and you can see the oscillations has increased. It is almost becoming unstable, because the output is getting higher and higher, right. So, as soon as now I want to bring down the oscillations. So, I have introduced Kd to be 10. Okay. Again, these are all these I am doing from just visualizing the effect. Okay. I have not done any theoretical analysis yet. Okay. So, now Kd will become Kd, I am putting it to be 10, and as soon as I bring in the derivative control, you can see that the drone is flying steadily. Okay. The oscillations have come down, but of course, the steady state error still remains, and therefore, I will give a I component now, Ki equal to 10, and you see the steady state error will approximately become equal to 0. Why do I say approximately? Because see, the drone is moving along the xy direction also. Okay. So, it is not exactly getting to the reference of 1.2 meters, because the other controllers are also playing a part, and this is deviating from the along the xy direction also. So, from here you can now understand that intuitively PID controller design is quite intuitive actually. You can look at the response and then design the PID controller. However, for all systems you might not be able to do it. Okay, because if you are suppose working in a system which if you run with a wrong PID, it might break down also. So, you cannot do it always. You have to be careful in those cases. You have to go for analytically finding out the transfer functions or using Ziegler-Nichols method that we have talked about. Now, I hope that with all this you have gained the knowledge of PID controllers, and you will know how to implement PID controllers from now. Okay. Now, this actually brings us to the end of the classical control part for this course. Moving forward, we will get into the modern control part of the course, and we will start with what is known as state space modeling of a system in the next lecture. Thank you.